And we stopped actually at the three-dimensional generalization of vorticity. We said that while in 2 dimensions vorticities could be concentrated in a single point, and we have point-like vortices, of course we can have also extended vortices if they collide and form some configuration. But the minimal thing which is consistent with our equations is this point-like object. It's kind of a general rule that the point-like object in, say, 2-dimensional space you can view as a 1-dimensional line perpendicular to this 2-dimensional space if you try to generalize it to 3D. It's a little vague formulation, but the precise thing is that we introduce the vorticity, which is a vector, and which is defined as epsilon alpha beta gamma d beta v gamma, and it satisfies automatically. It's purely kinematic constraint that the divergence of this guy is 0. It's literally like with the Maxwell equations. In the Maxwell equations, you have a pair of equations which is, in a sense, kinematical, which just tells you that the field strength is expressed in terms of vector potential. But you have also a dynamical equation. Another pair of Maxwell equations is dynamical. They follow from the Lagrangian. Here it's also the case that, so this is the kinematic constraint, and the general solution, the minimal solution of such constraint will be not that we have the naive thing would be to take some component of omega and say that it is proportional to the delta function. So the naive solution of this would be just to try some constant vector multiplied by the delta function. In this case, the vorticity would be, it's a wrong thing, what I'm saying. What I'm saying is wrong, but it's interesting to contrast it with the right answer. What I'm saying is that if you try something like that, some constant vector multiplied by the delta of x, that's wrong. Why it is obvious that it is wrong? What's bad about this assumption?
Is it non-zero divergence?
Yes. If you take a divergence, you differentiate the delta, and it's so you cannot concentrate the vorticity in a point. A priori, you could think that it's possible to have point-like vortices also in 3D, but it's not the case. And we found that the right answer is that you have a closed contour, and you integrate basically. It's basically the integral delta of x minus y dy alpha, contour integral around C. The explanation for those, if you feel some difficulty with this notation, it simply means that you have parameterized the contour, and it's an ordinary integral from 0 to 1, dy alpha over ds, delta of x minus y. That's more or less the definition of this contour integral. And you can easily see that if you differentiate it with this, if you take the divergence, you get the d alpha here, and this is complete derivative, integral of which gives you 0, because there are no endpoints. I'm going quickly here because we discussed it already last time. And now you can try to, so we have this kind of a rings of vorticity, or they can go, if you have walls, they can also end at the walls, depending on the boundary conditions which you have. And the velocity, you can actually now calculate the velocity generated by the vortex ring. For that, you have to solve the equation well, it's actually not difficult. Well, when you treat this equation, it's useful also to remember that the second equation is d alpha v alpha equals 0. And it is rather easy to reduce these two equations to the Laplace equation. I will I will very briefly, we don't have time for this, and it's not particularly interesting, but you can write down, to solve this equation, you write it down as epsilon alpha beta gamma d beta psi gamma. Then this equation is satisfied. When you plug it back here, you have the equation Laplacian of psi alpha integral delta of x minus y dy alpha. I recommend you to try this, and if you have difficulties, ask me for help. But it's more or less straightforward, and you can actually easily figure out what the answer is. The answer is the velocity of a single vortex line, the velocity produced by a tornado, is something like it should contain epsilon function, and it should contain the derivative, and it acts on the integral of the solution of the Laplace equation, which is just x minus y. Excuse me, it's gamma here. X minus y, and you integrate over c, and that's the equation which you get from here. Now, to find the motion of the vortex ring, you assume that the shape of the vortex ring depends, is given by some. At each given moment, t, you have a parameter s, so you have, at the moment 0, you have this ring, at the moment, next moment, you have that ring, and so on. And again, I'm going quickly here because it's not central to our discussion, but it's worth knowing. There are a couple of beautiful things which I can just tell you about, but not really discuss in details. So what you do then is just you write down the equation dx alpha dt is equal to v alpha of x of t and s. And this equation, this is precisely the three-dimensional analog of the Kirchhoff equation. Except in some very simple cases, it cannot be solved analytically. So people, when they are interested in vortex ring, they do numerical simulation of this equation. there is one interesting thing which I mentioned before we leave this subject, and that there is a very fascinating conserved quantity which exists in this. There are actually two interesting things which I have to tell you. One, and they both are relevant for the vortex theory. One is that if you can form in 3 dimensions the quantity H, which is called helicity. Which is just the scalar product v alpha of x and t, omega alpha of x and t, d3x. Now, it's again a home exercise, not difficult at all, to prove that if you use the Euler equation for v and the vorticity equation for omega, which we derived, then dh dt is equal to 0. So helicity is conserved. Now, by the way, what would justify the name of helicity here? What I mean is, what are transformation properties of these things? I mean, is it scalar or not scalar, and so on. So what would you say? What is how these things transforms under rotation and reflections? That's the question which we always have to ask about new quantities. So any suggestions here? Yes, go ahead.
Is it a pseudoscalar?
It is. Why?
Because it's a dot product of a regular vector and a pseudovector.
Yes, why it is. That's right. This is a true vector. This is a pseudovector. So under reflection, indeed, it will change sign. Why? Let's remember why omega is a pseudovector. How v, I'm repeating this thing again and again during the course, but it's indeed important to have to get used to this. So how v alpha of x and t transforms under reflection. So this solution goes into what under reflection? It's trivial question actually. So what we have when we have symmetry under reflection, it means that well, remember we had those terms d beta, d alpha. So what should we do if we reflect x? Symmetry under reflection means that reflected velocity distribution should be also a solution. So just look at this equation and you can read from it how to transform not to spoil the equation. That's basically the principle. You see what you can do. So suggest something, and then we will see if it's right or wrong or correct.
Negative v alpha of negative xt.
That's right. Actually, the new v alpha, the reflected v alpha, is minus v alpha of minus x and t. When you do this and plug it in, this term changes sign. This term also changes sign because it contains a derivative. So that's how the normal vector transforms. how helicity transforms. Thus, again, you can read. You see, this is nothing to be memorized or something, but you just look at the equation and see. It's not the, it was not told you by your superiors that it must be a pseudoscalar. You just look at the equation and see what it should be. You see, if you make a wrong assumption, you spoil the equation. So you try to choose the transformation which doesn't spoil the equation. That's the philosophy of it. So what happens to omega alpha tilde? The stuff written on the blackboard is sufficient to answer this. Again, try something. Which formula we should use? Obviously this one. Okay. So what it tells you, this formula? Under reflection of x, v changes sign, derivative changes sign, so omega doesn't change. The answer is omega alpha minus x and t. And this is what we call, that's just a definition. You can call it any way you like, but the standard name is that this is called the true vector, and this is called a pseudo vector. And correspondingly, helicity, which distinguish between left and right, I almost said right and wrong, but it's not the case. It's just it just changes sign. So now, what it means geometrically is very interesting. For that, you can calculate to understand it. By the way, before I go to this formula should remind you some formulas which you encountered in other part of physics. Any association? Not this one. That's typically specifically hydrodynamical. But this formula, all this stuff is something you in some form or shape you encountered before. Well, if you when you were taught electromagnetism, it's magnetostatics. When you have a relatively low velocity of particles, they generate currents, magnetic fields, and relation between currents, magnetic fields, and vector potential is precisely the same as the one here. And I suggest that you, again, as an exercise, you just try to establish firm connection between magnetostatics. Who is who in magnetostatics? Anyway, returning, I can't, although we have to move forward, I can't resist describing you one very beautiful thing, which exists in helicity. Let's take two vortex rings, C1 and C2. Then the helicity, there is a term in helicity which contains and there is also, of course, self-induced helicity for each, but that will not interest us. This part, however, is very interesting. It gives you this relative helicity. is proportional, if we look at this formula, it will be proportional integral C1 dx alpha integral dy beta epsilon alpha beta gamma x minus y gamma divided by x minus y to the cube. And actually I will normalize it as you will see y by 4 pi. And this is the integral C2. It's pretty terribly looking integral actually. But in fact, it is easy and quite fantastic. This integral equals to, first of all, for any smooth contour, it is an integer. Okay? And moreover, this integer is nothing but the way these two contours are linked. It's what is called the linking number. So you have the fact that it is an integer means that that it is also a topological invariant. Under small deformation, it is not changing. And again, it might look to be a terribly difficult statement to prove, but I will show you that you can do it in a few lines. Still, it's one, I would say, it's what is called topological invariant, the quantity which doesn't change under small continuous deformation. And it's the simplest representative in the family of topological invariants. Topological invariants permeate physics, especially modern physics and particle physics, standard model, etc. And this is just the and mathematics as well, of course. It came from mathematics. Actually, it was Gauss who first realized this. And, now, the way to prove it is very simple. You take. I will do it schematically and will be pleased to do more details. You attach an arbitrary surface to, say, C1, and you have C2. And when integrating by C1, you use the Stokes theorem, and you reduce it to the integral over this surface, delta of x minus y, and integral over, so you have dy alpha element of the surface d sigma alpha y, and that's about it. And you see that the delta function clicks if the contour C2 crosses this surface. So if it doesn't cross the surface, this is just the direct application of the Stokes theorem, which leads from here to here. And once again, I will be absolutely happy to explain it to you in details, if you like, but now we don't have time for that. You see, if the contours are not linked, like C1 and C2, then the delta function doesn't click and the integral is 0. Helicity contribution is 0. If they are linked like that, it's 1. If the one contour winds around the other, okay, then it's basically the number of time it winds. And that's what is called the linking number. And the integral counts this linking analytically. That's very beautiful, I think. And physically, conservation of helicity, which again, I have to leave for you to You see, it's just straightforward calculations using the equations of motion, which gives you this integral equation. It means that smoke rings, when they are linked, they cannot unlink. In fact, they can when you take into account viscosity, etc. But in ideal fluid, they cannot. And that was, I mentioned it already, that was the basis in the 19th century for it was a acute hypothesis by Kelvin, Helmholtz, that by very great people, that atoms and molecules are just different knots. You see, they thought that stability of matter is related to this stability of knots. Okay, so that's quite fascinating subject, and as I said, it's just the very surface of it, the very beginning of it. Then you have a fantastically beautiful and non-trivial topological invariance in various situations. All that began with this Gauss formula, and there is also a beautiful, the so-called Euler character, another topological invariant. And in modern physics, there are plenty. Okay. There is also another, before I still cannot leave it, as it is, there's another important conserved quantity in ideal hydrodynamics. Ideal means the one in which we neglect viscosity. And this is the we can introduce the so-called, apart from the helicity, we introduce also another quantity, which is the integral, which in principle could depend on time. And you take the contour and you integrate around the closed contour the velocity. This is sometimes called circulation. So this is the circulation, and the statement about the circulation is the following. The statement which we are going to prove. And all these proofs are simple if you know how to do it. First of all, if we fix the contour in the fluid, then nothing special. So you fix the contour C, and you look at the circulation around this contour. It's not an integral of motion. It's not constant. It changes with time. However, there is a more subtle. The statement is more subtle. If you allow this contour to change with the fluid, namely, imagine you use some drops of dye to denote this contour, and then it moves with the fluid and changes its shape. And velocity also changes. And then together, this circulation, when you take this together, the motion of the contour and the change of the velocity, it actually remains constant. And that was called Kelvin circulation theorem, and we will prove it very quickly now. So we have to see how this thing varies with time. We have, I shall rewrite it as an integral over ds. dx alpha ds v of x on t. Okay. And let's look how it varies when we take the change of the contour. So suppose you vary a little bit x alpha of s. Let's forget about time at the moment. Let's just vary this integral. You have you change the contour, and so we have to calculate the variation of this integral. But we already have done it, actually. When we had if you don't remember, we'll have to do the same job twice, perform the same job twice. But we actually looked at the variation of these guys. And the variation was just ds, dx alpha ds, delta d lambda v alpha, delta x lambda, plus and so on and so forth. So, but if you, it's a good idea to remember these things. Remember what we did when we talked about the general Hamiltonian systems. What kind of quantity we calculated? Okay, I will continue calculation. These calculations, you may interrupt me and tell me what the answer will be and what we have been doing already. So there is this term plus the term d delta x alpha over ds v alpha. And then we integrate this by parts. We will get an integral ds d alpha v beta minus d beta v alpha, integral delta x alpha dx beta over ds. So what we the major difference, the fundamental difference between the calculation we did in the Hamiltonian case and this one is that we called, in the Hamiltonian case, we called these variables y. Now we call them x. And there is nothing more than that. So what was the meaning of this formula in the Hamiltonian system? What?
Doesn't it come from the variation
Of what?
No.
Well, remember we had the general Hamiltonian system we said is the system in which you have some vector potential minus the Hamiltonian. And that gave us, now if you see the variation of this thing and variation of this thing is absolutely the same. So we have, except that we called, how we called in the Hamiltonian system, how we called this term. Now we call it vorticity, but how we call it then? It was the symplectic form which we discussed. Okay. Now one more step, and we're done with it. Namely, this formula shows how this thing varies when you vary the contour. But now let's take the time derivative of gamma for a fixed contour. For a fixed contour, we will have a very simple thing, dx alpha over ds, and here we'll have the alpha dot. And delta t. Now, if we delta x alpha, now we have to combine two things together. So the circulation changes for two reasons, and these two reasons cancel each other. Reason number one, the velocity here changes with time, and that gives us v alpha dot. But also there's another reason. You don't have to take these two reasons together because we are considering infinitesimal transformation. The other reason, if at the moment t the contour was like that, it becomes slightly different at the moment t plus dt. So what kind of delta x alpha? It becomes different because the fluid moves, and we decided to look at the circulation, at the contour which moves with the flow. So the only question is, what is delta x alpha here? So we have delta x alpha, how it is related to dt. It's a trivial question, actually. In other words, what kind of delta x alpha we should substitute here to take into account the fact that the contour, that our dye actually moves with the flow.
V alpha delta t?
Yes, exactly. So it's v alpha dt, or delta t. And now what remains is very simple. We have the equation v alpha dot plus v beta d beta v alpha is equal to minus d alpha p. I want to rewrite this equation in a slightly different way. I shall add and subtract the term d alpha v beta plus, of course, d alpha of v squared divided by 2, d alpha p, and the last transformation is this. This form of the equation is very useful, and I'll tell you why in a moment. But when we add together these two changes, we have precisely this combination which appears in our expression for gamma, for the derivative, for the complete derivative of gamma. Complete means consistent of changing velocity and changing the contour. The only thing, if we use this, we can we have this term, we have this term with this formula, okay, and as a result, we get minus integral over the closed contour of d alpha of p plus v squared divided by 2. And this is 0 because this is a complete derivative. So, and that's what is called the Kelvin theorem, Kelvin circulation theorem, which is very useful for qualitative analysis of the flow. Total derivative of, or Lagrangian derivative, if you want, v alpha dx alpha is equal to 0. By this derivative, once again, one means that the contour itself depends on time. That not only velocity depends on time, but the contour depends on time. If, as I said, if the contour is fixed, nothing interesting happens. This equation, by the way, this form of equation will be very useful for us. It tells you, among other things, it tells you that if the flow is time independent and irrotational, so let's suppose that we look at the stationary flow, and let's look at the irrotational flow, which means that Tst is 0 everywhere. Then what can you say about it in this case? What kind of conclusion follows from the equation? For irrotational stationary flow. Just look at the equation. Actually, there's an error here. It's alpha. And give me your conclusions.
Well, the alpha dot equals negative d alpha p plus v squared.
The what? Say it again.
Sorry, so I mean, you just set the middle term to 0.
Yeah, middle term is 0. This is 0 also. So the thing which we conclude is that this is, it's called the Bernoulli equation. And it's for irrotational flow. We will derive it also for general flow in a second, but at the moment let's look at this. And I will tell you all those things like Kelvin circulation, like helicity conservation, like Bernoulli equation, they all are very good for qualitative analysis of the flow, apart from being quite interesting by themselves. And I will give you a simple example. I already mentioned this example briefly before. Let's suppose that we have two fluids, say inside some walls, and one part of the fluid moves with velocity v, and another part with this one moves with velocity v, and this is v equals 0. And this is a possible solution of the Euler equation. I mentioned to you a slightly more general case when you have a wind over the sea. But you can just as well can have the same fluid. Now, the claim is that this motion is possible but unstable. And the Bernoulli equation shows this without any calculations. You can, of course, do the calculations of the type we did with small variation of the velocity. By the way, this type of calculation for this case you can find in Landau and Lifshitz. It's called Kelvin-Helmholtz instability. I will not do the calculation. I instead show you how Bernoulli predicts instability. And you just make a little bump here and see what happens. And here is v is equal to 0. And here is we have v. If we made a bump, velocity here is larger, and the pressure which acting in this direction is also larger. So this small bump, the Bernoulli tells you that the larger is velocity, for larger velocity have smaller pressure, and this bump will start growing as a result. Okay, and there are multiple applications of Bernoulli for some simple qualitative conclusions. But for more quantitative, you need, yeah, go ahead.
So what do you gain from looking at that bump that you don't see just from saying that the pressure differs by a factor of v squared?
No, you see, the point is that the pressure in this bump becomes larger because velocity here becomes larger, so that the flow is, the continuity is, velocity becomes larger, the pressure here becomes smaller. That means that the pressure here becomes larger and push the bump up. So that's the very quick explanation, but I think it will be instructive for you to read the chapter in London Lifshitz where they carefully they wrote down the Euler equation, looked at the small variations of the velocity, and see that this thing, they did it for different density in general and find complex frequencies. Okay. We have to move. Oh, yeah. No, I cannot move. There is one more general theorem which we derive from this equation. So this was for irrotational flow. But now let's look at the generic flow. Let it be still stationary. Non-stationary also can be done, but it's not so interesting. Let's consider stationary, but let's not assume that the flow is irrotational. And the thing you can do now to get an interesting equation, so now vorticity is non-zero. There is still some statement about this combination which can be made. Look at the equation and think how can we drop this term, and think how can we simplify this. How can we drop this term with vorticity? What should we do with this, with the equation, to eliminate this term? Think for instance, yes?
So could we expand the right-hand side with the d alpha v squared?
That would be just a tautology. You will cancel this term. It's nice to have the equation in this form because it has physically meaningful combination, which is vorticity. And also it's anti-symmetric. If you multiply it by v alpha, you get identical zero at the left side. Because when you multiply it by the alpha, you have symmetric tensor multiplied by the anti-symmetric tensor, and that's 0. Okay? So we multiply it by the alpha, and we get the relation v alpha d alpha of p plus v squared divided by 2 is equal to 0. it's a weaker statement than this one. Of course, if it is constant, then it's trivially satisfied. But generally speaking, only this relation is satisfied, and we have to understand what it means. Try to think in terms of streamlines of the flow. Yes?
How can we set v dot alpha is equal to 0?
Oh, I was talking about, it's not 0, of course, it's dT square, but I was looking at the steady state flow for which v dot is 0. So it's just an assumption that v dot is 0. If it is not 0, it's always also an interesting equation, but I will stick to this stationary flow at the moment. So the question is, what is the meaning of this equation when you have some function d alpha multiplied by some function is 0? What's the meaning of this?
The gradient's always perpendicular to the alpha.
Yes, so it means that if you have streamlines in the flow, streamlines are the lines such that tangent velocity at this point is tangent to the streamline. That's the definition of the streamline. Then along each, and so any flow can be represented as a collection of streamlines. This equation means that the Bernoulli combination along each streamline is 0. It may be different between different streamlines, but on each streamline it's 0. It's a weaker statement in irrotational flow. It will be also the same on different streamlines, but it's not the case in general. Still, it's very useful even in this form. We will see this in in our next in the next part of this lecture. Okay. So a collection. So to summarize this part, we have a collection of beautiful things, in my opinion. We have linking numbers. We have helicity, conserved helicity. We have conserved circulation, and so on. And it's true that the application of this is somewhat limited, because in many cases you have to account for viscosity, but still. Well, there are also cases in which viscosity is identically 0. This is the superfluid helium at very low temperature. So it's the Euler equations. They are, although skeptics call them equations for the dry water, but it's unfair. All right, now let me show you how to solve the problem. We return to two-dimensional case temporarily, and how to solve the problem of basically of airfoils, of how we have flow past some obstacle. What are the forces acting on this obstacle? Do we have drag force or lift force, and so on? So the general questions which will interest us in this part will be how to pose these problems of flow moving past some body. And we will start with a very simple situation. Then you have a disk or a cylinder in 3 dimensions, and you have some flow past the cylinder. And then we will generalize. It does look very much like aircraft wing, but it's important step to learn how to solve these problems. And once again, we will assume that at infinity, velocity is fixed. So, and well, let me introduce a few notations. So we will be looking for the velocity. We will assume that the flow is incompressible. And we can actually write down the alpha in two ways. It's epsilon alpha beta d beta psi. And psi is psi is what is called the stream function. And we want to solve this equation, but we also want to solve the vorticity. We will consider irrotational flow at this moment. And we have to solve this equation. If we start solving this equation, that solves it identically, but we have some equation here. But we also can have an equation that it's equal to d alpha phi. That solves this one, but leaves this. So we have two, this is called the stream function, this is called the potential, and they have, so once again, d alpha phi is epsilon alpha beta d beta psi. Now I want you to see a very important analogy here, not analogy, but the statement here. In some different form and different notations, you certainly know these equations from your math courses. And what it reminds you, try to attach, try to make the connection with what you know. It's not the first, I claim that you encountered, without knowing it, you encountered already this equation. Well, let's write it down in components. Is it better this way? So, maybe in the reason for the difficulty is that in your math course, I guess it was used not with the Greek letter, but with the Latin alphabet. Instead of phi and psi, you had some U and V, perhaps. Any? Yeah, it's how is that?
But it's the Cauchy-Riemann.
Cauchy-Riemann equation, exactly. Which means what? So it's indeed it's the Cauchy-Riemann equation written in this form. And remember what those Cauchy-Riemann tells you. What's the meaning of this equation? Well, you see, let's look at what is called complex potential. That's a useful thing. Phi plus I psi. Then you will have d1 phi equal to d1 phi plus I d1 psi. And d2 phi d2 phi would be equal to d2 phi plus I d2 psi. And now I use this thing, and I would say it is equal to d2 plus I d1 psi, and this is equal to minus d1 plus I d2 psi. So the result of it is that d1, if I did me plus I d2 applied to the complex potential, is actually 0, which means that if you introduce complex variables and you introduce complex function, this equation is nothing but, actually if you write it down in complex coordinates, it is very simple. It is just tells you that d dz bar of phi is 0, and that the solution of this equation is simply that phi, the complex potential, is some analytic function of z. So if we take any analytic function, we in this way solve this equation. And basically, as I said many times already, the epsilon tensor is just coordinate notation for the letter I. In Cartesian coordinates, you will have epsilon alpha beta. In complex coordinates, you will have multiplication by I. So any analytic function, you can now say it's convenient to introduce. Notice, by the way, that if you have a plus here and a plus here, that this is not the derivative with respect to z, but with the derivative with respect to z bar. That is clear from, well, roughly speaking, when you differentiate, you change the sign of I. Or we actually, when we discussed the Kirchhoff equations, we said that under rotation, this transforms like this one. That's just a mnemonic rule, how to remember all those signs. Of course, you can just use the standard formula to, you write it down as ddz. It should be dx1 dz bar, ddx1, and so on. So you can change coordinates in a standard way, but it will save you some time to write down the answer immediately. Okay, it's convenient to introduce this complex velocity with a minus, and this complex velocity will be the derivative of complex potential. That's what replaces all these formula in complex notations. So far it's a simple math, and now we have to return to physics. First, and it turns out it's convenient to determine first the complex potential. What we know about it. How it if we have a flow past the cylinder or past the disk, what is the at infinity, how it behaves asymptotically? Suppose we have velocity u infinity. What is the behavior of phi? At infinity. we want, yes?
It's the same as if the circle wasn't there, so you just have,
Say it again?
it's the same as if the cylinder wasn't there.
Yeah, so but the question is what is how this function, what is the asymptotic behavior at infinity? What would be your answer?
This one is,
Well, it's just sort of, yeah, just you have this u infinity multiplied by z. It's so that the derivative will give you simply u infinity. It cannot contain higher power of z, therefore it will spoil the whole picture if it has. But since we have a unit disk here, we have to find the analytic function, the most general analytic function in this domain. As we said, should contain that plus what else it can contain, which doesn't contradict boundary conditions.
Some constant.
A constant, okay, it will drop out. What else? But it would be not good enough to have only constant. But I don't mind. You are right, it's constant is possible. So what else? Any analytic expression which will not contradict anything. What would it suggest? Saying at this stage there are infinitely many possibilities. So, and I ask you to choose one. Just something. What kind of function could it be?
So we have a no-slip condition at the boundary of the
We
circle.
will come to the boundary condition in a moment, but suppose let's postpone this without boundary conditions. What would be a possible term? What would be possible terms after the constant?
Anything that goes to 0 at infinity.
What?
Or I guess analytic functions can't go to 0 at infinity.
Yeah, but give me some example.
So anything, yeah, that will grow much slower than the linear term.
Example.
1 over z. Yeah.
1 over z, good. It has a so why the singularity is not important at z equals 0? Why it is singular? You see, if the function, first of all, the standard theorem of complex analysis is that if the function has no singularities and tends to a constant at infinity, it tends to 0 at infinity, it's 0. It must have singularities, okay? And it does here in your proposal. But why it should not bother us, this singularity? Yes?
because the singularity is within the area, it's not existing.
Exactly. It is inside, and inside there is no hydrodynamics. We need only the solution outside of this. But then all is permitted in a sense.
So you can have any pole.
As,
less than.
yes,
Yeah.
yeah. All is permitted, and you can have the famous phrase from one of Dostoevsky's heroes, all is permitted if there is no God. So here, if there is no boundary conditions, all is permitted. And this is called, by the way, the Laurent series. The Taylor series is expansion in positive powers, but we cannot have Taylor term because they will spoil everything. And this is the Laurent the Laurent series. Now we will show that in fact only this term is legitimate. It remains when we impose the boundary conditions. Well, let's begin with. First of all, we have to decide what are the boundary conditions. So we have to impose them on the velocity and then translate onto this potential, onto this complex potential. So what would be, in your opinion, the boundary condition on the velocity? Yes, please.
The velocity is 0 on the boundary of the sample.
These.
0 along this line.
It's a natural guess, yes. But if you try, the problem with it is that if you simply set velocity everywhere 0, you will not find any solution at all. If the analytic function is 0 at the boundary, it's 0 everywhere. You see, it's very restrictive. But although we will, in a while, we will be considering such boundary conditions also in other cases. But at the moment, we need a somewhat. We try. It's, as I said, it's a very natural try to say that the boundary condition is just velocity 0 at the boundary. But we find no solutions like that. You can see that no functions of this type will have this property. And why? Remember, we are talking about ideal fluids. So what would you say, how to relax these boundary conditions?
Should be tangent to the...
Yes. You see, since there's no viscosity, it's okay to go in a tangent way. So the condition is that perpendicular velocity at the boundary is 0. The velocity, the boundary condition which you mentioned, which is called no-slip boundary condition, then velocity is 0. It's indeed applicable, but for viscous fluid. In the case of viscous fluid, indeed, the fluid sticks to the boundary and we have no slip. But for the ideal fluid, it's like that. And it's very easy to write it down in terms of complex potential, because it simply means that the radial component of the velocity, is 0. For the disk, the radial component is just so. How to formulate it in terms of complex velocity? First, in the real components, what is the condition that radial velocity is 0? How would you formulate it?
So if it were in R2, then it would be R dot DDR equals 0. So x ddx phi plus.
Well, you see, we have we have a radial component of the velocity is just the projection of the velocity onto radius vector. It should be 0. In complex notations, it's just, we discussed it, that the complex product, the scalar product, is just the real part of the complex product. So you have and this should be satisfied, by the way. It cannot be, if I try to impose something like that, everywhere, that would be a disaster, no solution. This is only if I take absolute value of z equals to 1. And that's the boundary condition we need. Now, 1 is the radius of our disk. And now we have to solve this thing. And the solution is quite simple. Let's take, you first drop all other terms, and then we will see that they violate everything. Let's consider this thing. Excuse me, this is phi. Let's try this, the simplest thing we can think of. The complex velocity, we have to differentiate it. It's u infinity, 1 minus 1 or z square. Zv of z is now what I shall do, the next line which I need. What should I now substitute to check this relation? What should I be testing now? It's just the transformations which I... So what, according to our boundary conditions, only tangent velocity at the boundary, we derive that this is the same as this. Of course, you can just express z as x1 plus x2 and so on and obtain this. I got this relation. But then what? What I should plug in to test this? Where is the boundary? What's the equation for the boundary?
E to the I phi.
Exactly. I shall use a different letter. Phi is occupied already. So at the boundary, it's you see, it's purely imaginary. So the real part, so we managed to satisfy this boundary condition with it. Well, that's not the end of the story, but it's the end of the class problem. So the last comment is that if you try to add the 1 over z square term to here, you immediately see that that this expression will contain trigonometric functions of 2 alpha, and they will never cancel at the boundary. So you just check that none of these terms is able to satisfy the boundary condition. That's very simple to check. Well, just for example, for 1 over z square, you in complex potential, you take phi prime, which is 1 over z cube. You multiply it z phi prime of z, that 1 over z square, and this is e to the minus 2i alpha on the boundary, which contains both real part and imaginary part. It's only for the first, for these 3 terms, you can satisfy the boundary conditions. Okay, let's stop here.